Perfect timing. All right. So one of the things that we'll be talking about in this lecture today is going to be dealing with the idea of power. You'll notice that power can be easily confused with energy. And one of the first things I want to start off with is by saying power is not energy. It's called power, not called energy. So it has a different meaning. It has a different definition. The first thing to get out of it is the definition is this. Power, by definition, is going to be the amount of energy transferred per time. So you can look at that definition and you can actually get the equation straight out of the definition. Power is equal to the amount of energy transferred, aka delta E over delta T. So you'll see that that is change in energy per change in time. The other way to write this is actually going to be W divided by delta T, W being work. And remember, one of the things that we defined was work was the change in energy by a force. So you start to be able to make that connection very easily. And we'll look at a problem that will go right along with the quiz that you guys just took. The other thing to note about power and looking at this, the unit that goes along with power is going to be a joule per second. And a joule per second can actually be rewritten as the standard international unit, the watt. Watt. And that is abbreviated a W, which now starts to get really confusing because you'll notice right away when you look at this, you see a W here and you see a W there. Those are two different W's. They stand for two different things, right? One is a watt, one is work. So just because you see a W, you need to make sure you understand the context. One is a unit, one is a variable. They are different. The other difference that throws a lot of people off is when you start talking about watts. When people hear a 60-watt light bulb, they usually associate that with the amount of energy. No, that is the amount of energy per time. So a 60-watt light bulb really refers to 60 joules that a light bulb will use per second. So that is what we have whenever we see that. The other case that we will run into is the other form of, or the other unit that we associate with power, and that's horsepower. So the other thing that I like to bring to your attention is 746 watts is equal to 1 Harry Potter, or I mean horsepower. So we run into this idea, yes, 1 horsepower, our usual unit that we associate with cars, is referred to as 746 watts. And if you ever really want to get good at unit conversions, I always like to tell my students, go under Gran Turismo or any racing game and change the units from American to standard international. And then you'll go into a car screen and you'll be like, is this car any good? And you'd go look at power and you'd see that it's rated at like 15 kilowatts. It's like 15 kilowatts. 15. How many baits? Is that good? That's a lot of kilowatts. And you start to realize after running the conversion, you're really talking about a really, really bad car. I mean, like a toy car. Yeah, so you start really realizing, wait a minute, yeah, that doesn't work too well for us. So again, I think it's a really interesting connection. We'll also be talking a little bit more about this unit in the form of energy, being that right now, the computers that you use usually run on 500 to 700 watt power supplies. Again, people think power supply and they're thinking about energy. That is how much energy it uses per second. So you hear 500 watts and you're thinking, wait a minute, that's 500 joules every second that thing's turned on. starts to become a lot of energy. And we will talk more about this. We'll talk about candy bars in this sense. We'll talk about activities that talk about wattage. That's how much energy you are using, transferring per second. We even might give you the challenge of seeing if you can output a horse. And we'll talk about how you can possibly do that. So, all very interesting. Let us talk about how this equation can be used in an example problem. So, the equation that we will be looking at here, or an example problem that I think is really easy to understand once you take a greater look at it, is very similar to our quiz question. What we are going to have here is we're going to have a ball that is sitting on a spring. That ball is going to be 1 meter above the ground. So we can look at it here. And that ball is then going to be shot off of the spring. And that ball is going to be, this is not to proportion, but you'll see that that ball will be 3 meters in the air. Things to note about the ball: the mass of the ball is going to be equal to 1 kilogram here. And just for kicks, the time is going to be 0.1 second. This is the time for the ball to be released from the spring. And of course, one of the questions that I can ask is I could go here and I could say, what is the power output of the spring while it is releasing off of there? And so this is our example problem. This is going to be very similar to something that you might run into your homework with tonight. So how do you do it? What's the first goal? Well, the first thing that I see is I see this right here, and this is my goal. So I go to the equation, I say power of the spring has to be equal to the change in energy of the spring per the change in time. I'm happy because I know the change in time already. That's given to me. However, I don't know the change in energy of the spring. And whenever we get to this point, we always have to ask ourselves, what is the easiest way to get the change in energy or the work done by the spring? Anytime you hear change in energy or the work done by the spring, you need to be clever. And the first thing that you do is you should move on over here. You should draw your LOL diagram. And the next thing is, because you are a smart system selector, you have to say, what should be my system if I want to know the change in energy of the spring? Well, as we've said before, if you want to know the change in energy of some object, the easiest way to do it is take it out of your system. So normally you would have put it in, take it out. We're looking for the change in energy, we're looking for the work done. Make it really simple, take it out of your system, so all we have is the ball and the earth here. Spring is on the outside of the system. Now, the other thing, moving on over to our picture, is going to ask, do I have any energy stored in my initial state right here? And the answer to this question can be twofold. Yes and no, dependent on how you set this up. If you put your zero marker down here, if you put your zero marker down there, you would say there is energy stored gravitationally at this point. However, if you wanted to, you could put your zero marker right there. And you can solve this problem as well. I'm going to make it easy on ourselves, and I'm going to put our zero marker where the ball is. You'll see how much easier this is by making this choice. However, your answer will still be the same if you use the 1 meter marker. Oh, I'm sorry, if you use the zero marker down at the bottom, it'll still be the same. We'll discuss that very briefly. So at the beginning, if our zero marker is going to be again right here, you'll notice that is there any EG stored? No. Is there any ES stored? No. Is there any EK stored? No. So you'll notice EG, EK, and ES are all 0 at the beginning. Why is there no ES? No spring in our system. So that makes it really simple and really easy. Now moving into our second portion, what type of energy is stored in the ball earth system here? You'll notice that it has a height. There is an EG at that point. You can solve that very easily using the givens as well. So you'd say there is some EG at that point. Is there any ES? No, the spring is not compressed. Is there any EK? No, the object is at the maximum height. And E internal, we are going to assume air resistance can be ignored. And so we have 0, 0, 0. And the moment I draw in this LOL diagram, you notice that there should be an arrow going into here. Work done by that spring. Hey, that's the value that I'm looking for. I am looking for the energy transferred by the spring. And again, because I selected my system this way, it's really easy to look at this and say, yeah, I can calculate that. I can calculate that purely by getting EG. And so we're going to do that very quickly. EG is equal to 9.8 newtons per kilogram times our mass times our height. 9.8 newtons per kilogram. Mass of the ball, I said, was 1 kilogram, correct? And the trick to this one, what is the height of the ball from here to here? Oh man, we lost the ball. What is the height of the ball from our 0 marker? In this case, it's going to be 2 meters. So we go on over here and we can then go calculate that, put 2 meters in there. And don't pull out your calculators. Please, you guys can do 9.8 times 1 times 2. 9.8 times 2 is 19.6. Whew, I was getting a little bit nervous. 19.6 joules. 19.6 joules. So, what's really nice about this is you'll notice that is the work done by the spring as well, because you notice that energy that was transferred in here is going straight to the EG. So that is the amount of energy that was transferred by the spring. And so now we go to our power equation. Again, power is the change in energy of that object over the time, or in this case, 19.6 joules over 0.1 seconds. Please do not pull out your calculator for this either. Dividing by 1/10 is the same thing as multiplying by 10. And so you run into this as actually being 196 watts. And so from here, you're like, wait a minute, hold on. That's like 3 light bulbs. So if I did this, I could power 3 light bulbs? Sure. For how long? 1 second. So you got to, of course, put it in perspective. Could you keep this up? Probably not. But it is a curious thought. Now, I want to briefly go back to our LOL diagram where, let's say, if we would have picked our 0 marker down there, how would this change? Well, that would mean I would have some EG at the beginning, correct? That EG would be calculated by doing 1 meter times 9.8 times 1 kilogram, correct? And so if we did that, you would realize that that is 9.8 joules. What's interesting about this is then in this diagram, in our second diagram, we are 1 meter above the ground than we normally were, right? If we go back to this, instead of now my 0 meter is here, oh no, there goes my table. If this was our 0 marker, we are now 1 meter above the ground than we normally were, which means this value right here is just going to have 9.8 joules more associated with it. So my question to you is, does this answer change? No, the work still stays the same. That 0 marker does not change our answer one bit. And so that is another, again, really nice thing about this. The reason why we choose our 0 markers to make our lives more easy in this case. So, any questions? What we just went over? So, our homework for tonight is going to be looking at more of these problems. That's not what I want.